Now let's talk about why partial derivatives are important for describing phenomena in thermodynamics. And so in our previous kind of half chapter where we talked about um, the microscopic meaning of entropy, we saw that we could develop a model, or microscopic model of entropy. Model of entropy. Okay. All right, and so for example, if we consider a van der Waals gas, so not an ideal gas, but a gas in which we, think about or allow there to be molecular interactions and also the gas molecules to take up space, we could derive a microscopic entropy model that looks like this. Four pi m internal energy over 3n h squared raised to the 3 halves, and then v divided by n, b divided by n, times u plus a n squared divided by v raised to 3 halves. All that's in the natural log, and then we have a 5 halves here. Okay? And so as a reminder, this b describes the size of the gas molecule, and then the a here describes the interactions between the molecules. All right. And so from this entropy model, if we wanted to gain some insight into how big the gas molecule is, or how are these gas molecules interacting with one another, what we would want to do is we would want to be able to measure what B and A are. Okay? So we would have to design some experiment in which we could, now that we have this model, we would have to design some sort of experiment in which we could track the entropy of the gas. And by doing that, if we track it under different, internal energies or volumes, we would be able to figure out what A and B are. And so in other words, to figure out what A and B are, we could track the change of S of an expanding gas. Okay? And so for that, to do this sort of thought experiment, or actual experiment actually, we could turn to our trusty model system of the piston cylinder. Okay? Where we start our experiment with some gas that's compressed. It's at temperature T1, volume V1, and then we somehow control the expansion of the gas so that it's at a new volume, and a new temperature. Okay? All right, and so for, let's say we could design our experiment or even model the expansion as a two-step process. So it can model expansion as two-step process. Okay? And so let's say the way we do the expansion, or the way we think about the expansion, is that we first isobarically heat the gas from temperature T1 to T2, and then we isothermally expand the gas so that its volume changes, but the thing that we would be measuring, though, would be pressure. Okay? So isothermal expansion so that the pressure changes from P1 to P2. Okay? All right, and so if we plot this out, so plot temperature versus pressure, the way we would think about our process would be we start at P1, T1, and then we keep pressure constant and heat the system so that it reaches T2, and then we keep the system at temperature 2 and we just increase the pressure somehow. Okay, so this is step 1, this is step 2. Okay, all right, and so that's the process that this gas would undergo. And so if we think about the change in entropy of the gas, so it would be the integral of ds. What we would be doing is we would be looking at how the entropy changes as a function of temperature while holding pressure constant as we go from some temperature 1 to some temperature 2. And then we would look at how the entropy changes as a function of pressure while holding temperature constant as we go from pressure 1 to pressure 2. Okay? Right? And so the idea here was that our entropy, we're saying it's a function of T and P. Okay? And so when we look at how the entropy changes as a function of one of the variables while keeping the other one constant, the way we describe that mathematically is just by looking at its partial derivative. All right, that's just mathematically what we're doing here. Okay, that's mathematically how we express the experiment we're doing. So we could do that with entropy. We could also essentially do the same thing in terms of internal energy as well. Just for completion's sake, I'll show you this. So one could also look at how internal energy changes as a function of temperature while holding pressure constant, and then look at how internal energy changes as a function of pressure while holding temperature constant as we go from P1 to P2. Okay? All right, and so, that's the experiment we do. All right? And so, once again, the goal here is we want to figure out what B and A are for gas, right? These are going to be constants that give us information about how big our molecule is and also how these molecules are interacting. Okay? And so our approach for figuring this out is that this right-hand side is essentially where we would put our measured data. And on the left-hand side, this is where we would apply our microscopic model, either for entropy or for internal energy. And the way that we figure out A and B, those molecular parameters, is we're going to adjust our model we're going to change the a and b values until this part of the equation best matches this right-hand side of the equation. And so we're going to fit our model to the data. Okay? So our approach is that we're going to fit delta S model to measurement data so that we could estimate A and B parameters of this van der Waals gas. All right, so that's the approach. Right-hand side of that equation, that's where we put experimental data. That's where we put the stuff we measure. Left-hand side, that's where we actually write out our mathematical equation. And then we just fit the left-hand side until it matches the right-hand side. But of course, there's one big issue here. Right? I said the right-hand side is where we put all our measured data. But the big question is, how do we get ds dt, a constant p, or how do we get ds dp, a constant t, right? As I've stressed before, we can't measure entropy directly. All right, we don't have any sort of device or instrument that will, if we pointed it at the gas, we don't have anything that would just tell us entropy is equal to X. Right? So we can't measure entropy. What we can measure, though, are things like pressure, volume, and temperature. So for things that we can measure, we call these measurables or observables. All right? And so, to overcome this issue here, where we need to find some way to actually measure ds dt and ds dp, right? What we need to do, or the solution to this, is we need to rewrite or recast ds dt and ds dp only in terms of stuff we can measure. Okay? And, well, of course, one would have to do the same thing for du dt and du dp. Okay? All right, and so really the main point of this chapter, of chapter 6, is we're going to show how we can turn molecular models of S, U, and other sort of kind of abstract molecular properties, things we can't see with our eyes, and how we could mathematically transform those into properties that we can measure, like pressure, volume, into functions of things like pressure, volume, and temperature. Okay? On the flip side, what we're also going to do is, well, actually one example of this is that entropy equation for the van der Waals gas that I showed earlier. What we're going to do is we'll show you how you could just directly turn that into an equation where P is just equal to nRT V minus NB minus AN squared over V squared. All right? So here, instead of having to figure out what to do with entropy, now all we have to do here is measure temperature, measure pressure, measure temperature, measure volume, and then we could fit our data to this equation, and that will allow us to get B and A. Right? That's the sort of approach that we want to take here. Okay? And we could also rewrite this in terms of molar volume as well. Oh, actually, A, V. Okay. All right. But of course, in order to do these sorts of transformations and derive these sorts of relationships, we're going to need to use some mathematical tools to do this.